morning, all. Myself, Dr. E. Meher Abhinav, a physical design engineer working at Sultan Semiconductor Private Limited. Today, I'm going to talk on the role of physical design engineer in VLSI design. So, agenda of my talk, I'll start with the overview of VLSI industry, followed by ASIC design ecosystem, physical design flow. This will be the major focus topic for today, and career opportunities for the physical design in VLSI industry. So, we got expectations in the registration. Like most of the people are participants are students of a BTech, and they were expecting regarding like the career opportunities in VLSI industry, and they wanted to know the concepts of physical design and even the current job regarding the current job market, etc. So I have made a flow with respect to this, and keeping time as a constraint. So I'll be explaining the main key points with respect to the physical design flow, because like a physical design flow, we have so many topics in this. So it's like a 4 months course, but over here I'll be mainly focusing on the key concepts with respect to the PD flow. So now all the gadgets showcased in the picture are made up of semiconductor chips. So we can see various gadgets, right? Like consumer electronics, embedded, IoT, the healthcare, and all. All the gadgets we can see in the screen needs a semiconductor chip. So why semiconductors? So semiconductors are more used. The main reason is the conductivity of a semiconductor lies between a metal and an insulator. And the major key point with the semiconductor is we can control the flow of electrons. So the current flow we can control. So by this a key point, key fundamental, the electronics have been started like till 1947. Till 1947, if you see the semiconductors was unexplored before the devices were with respect to the metal itself. So later on in 1947, like Shockley, Bardeen have invented a semiconductor-based transistor at AT&T Bell Labs, and they have got a Nobel Prize in 1956. Later on in 1958, the Jack Kilby and Robert Noyce. So these were the physicists who have invented the integrated circuit using the semiconductor transistors, and these were given a Nobel Prize for the invention of integrated circuit. So we already know what exactly an integrated circuit is. So millions of currently, like if you see in a very large scale integrated circuits, millions and billions transistors integrated on a single silicon chip. So, and later on in 1965, Gordon Moore has predicted a law like for every 18 months, the number of transistors integrated on a single chip doubles. So, after till 50 years, this prediction was valid, and it has been converted as a law, from prediction to a law. And he got IEEE Medal of Honor. So we already know like uh, the engineers, we don't get a Nobel prizes, right? So most like we have a Nobel Prize for engineers, we have IEEE Medal of Honor. So Gordon Moore got that, and later on in 1987, the Maurice Chang have in 19 okay, in 1987, the Maurice Chang uh, um he has founded a TSMC foundry, like a TSMC in Taiwan. So he has shifted from Harvard, and he has done his PhD, and he has researched certain works in Stanford, and he has shifted to Taiwan. He has founded the TSMC fabrication unit, and later on we know like Taiwan and South Korea were the leading countries for chip manufacturing. So this is with respect to the history regarding the semiconductors. So if you see over here, like if you want a single application, like example, if you take a mobile, if you take down the mobile, we can view various parts like accelerometer, audio chips, battery, camera, processor, gyroscope, touchscreen controllers, CPU, the GPUs, and all. So, to make a single mobile, so many companies will come into the picture. So, this is just an example. So, we can see the companies like Bosch, Samsung, Qualcomm, AKM Semiconductors. So, it's not like a single company will fabricate a total mobile. So, so many parts will be fabricated by different companies, and later on it will be assembled, and it will be marketed by the various companies like Oppo, Vivo, etc. Okay. So, this is a main slide, like with respect to ASIC design ecosystem. So, if you see over here, the first part, the parts over here from a need to the design. So, from here to here, it's totally with respect to the design aspects, and later on, this part is with respect to the manufacturing, the process part, and today, main I'll be focusing on synthesis, DFT, PNR, and sign off. So, if you take a mobile as an example, so first customer will come into the picture. He will ask like, I need a mobile with a camera with this much pixel, CPU. A GPU, and he will even mention a few specification. He will be giving a certain specification what exactly the customer needs. Later on, the architect, the design architects will come into the picture, and while they will take the needs of the customer, and they will make a specification, and they will even do the micro architecture, and they will make it to a smaller blocks. So why smaller blocks? So if you have a design with 1 million, etc., so we can make it as a flat, and we can run the design, and we can do the verification, and we can sign off very easily these days with using the current EDA tools. But if the design has more than 2 million transistors, so it will be a complex task for verification engineers, and the runtime of the tool will be very high. So time to market plays a major role. So we have seen in the semiconductor industry, like Nokia, it was a leader for mobile phones, etc. So they couldn't update, and they couldn't come in a correct time. So for that, they have lost the entire market. So same thing, like time to market is one of the important thing. So design engineers make the spec, they make a data flow, and they make the total architecture into a smaller blocks. So the smaller box will be the blocks will be given to the RTL design engineers. So here the RTL design engineers will come into the picture, and they will by using the hardware descriptive languages like Verilog or else VHDL, they will write the code with respect to the functionality. The whatever spec given by the design engineers will be taken as an input, and the RTL design people will be writing the code. later on it will be passed on to the functional verification team. So whatever spec example, if it is a bus, so if it is a 128 k bus, so example, so whatever it is there given by the design engineers, so the functional verification engineers will be checking whether with respect to my spec, whether my RTL code is working fine or not. So they will verify and they will be passing on to the synthesis team. So the synthesis team will be having various inputs. So one of the main input is the netlist, the RTL code given by the verification engineers. So the verified RTL is one of the major input for the synthesis. Second one will be if it is a low power or a multi-voltage design. So we will take UPF and libraries. So libraries, the standard cell libraries, if it is having a macro, so macro libraries and all, the library part is like the lib file is one of the input, and the timing constraints. So all the timing constraints with respect to the clock details, clock exceptions, and all will be there in our SDC. So these are three major files which we give for the synthesis. So, and the synthesis, before a synthesis was a separate team. Now, in the current trend, even synthesis is a part of physical design. So, there is no hardbound rule like people used to say till verification it is front end, and later on from synth it is back end. So there is no hardbound rule. But currently, if you see the Synopsys tool, so we have a design compiler for synthesis and ICC2 for PNR flow. So, but now currently Synopsys has released a new tool called Fusion Compiler, where they have merged the synthesis tool and ICC tool together, and they have fused together and made it as a Fusion Compiler. So for that, the basic input will be the RTL, and the Fusion Compiler tool will convert the RTL to the routed netlist. So we can do both synthesis and PNR by using the Fusion Compiler. So over here, if you see, the main synthesis is the conversion of RTL to a technology-dependent gate-level netlist, optimized gate-level netlist. So the RTL code, what we get from RTL design engineers or else functional verification team, is a technology-independent. So after doing the synthesis, the final output is optimized technology-dependent gate-level netlist. It is a technology-dependent with respect to the libs what we are using. So if I want a netlist with 5 nanometer technology, so I will be using the lib files with a 5 nanometer lib. So this is how the optimized netlist will be mapped. So later on, we will be getting a technology-dependent netlist. So over here, if you see the first job role of a PD engineer is like a synth. So there will be certain jobs totally focused on synthesis. So this is our first job role we can mention, and the DFT is a different vertical, so it doesn't belong to the PD part. So DFT is a different vertical. So what exactly the DFT people will do over here is they will take the optimized technology dependent netlist as an input, and they will stitch the scan chains. So the scan chain will be added over here in the after the synthesis part. So later on, again, we will be, after doing the synthesis, we will be doing the LEC. So we will be checking the functionality, whether my netlist is working the same or not. Like if the logic is changed, so again, we need to work on the send part. So even after adding the scan chains, we will do the LEC check to check whether my functionality is working fine. Okay. So after doing scan chain insertion, so later on we go for a PNR. So in PNR, what we do is first we will be doing a sanity check. So what and all inputs we will be getting from the synth, example, the STC, we will get a UPFs, we will be getting the netlist. So that netlist we take, right? So we will be checking whether my netlist is proper or not. So what and all issues we can see is like multi-driven nets, floating issues. So even we can see combinational loops. So all black boxes, etc. We can see such issues in the netlist, and we will even check the quality of our library. If there are certain cells having an issue, there might sometimes in a library what we see is like a pin spacing issue, diffusion issues with certain cells. So we can report to we can report to the library team. So the IP. In the physical design, we don't uh, do total full custom, means like libraries or its memories and all we don't design. So physical design is a semi-custom. So what we do over here is we will take the IPs from IP vendors, something like Synopsys, ARM, AMD, Samsung. These are major players with respect to IPs. So what I like standard cell IP or in some macro IP and all will be given by vendors. So why we don't do from the scratch is like creating a memory itself takes a good amount of time. So time to market is one of the important factor, right? So already optimized, characterized memory standard cells, etc. We will be taking from them and we will be using in our designs. So yeah, so in the PNR, we will be checking the quality of your netlist. We will be checking the quality of one lib, and we will be checking our SDC also if there are any exceptions to be added regarding the multi-cycle paths or else if any false paths, etc. So we will be doing that, and we will check whether our SDC is fine. So these are the sanity checks we will be doing before the floor plan. So from floor plan to routing, we call it as PNR, place and route. So after routing, we will be doing various checks like with respect to sign off. So one vertical will be with respect to timing. So other vertical will be with respect to the PV. So other another vertical is with respect to EM and IR. So these three are the major things we will be working out after place and route. So after all these three checks are fine, so we will be taking out. So take out is nothing but giving our GDS, the clean GDS to a foundry. So now foundry example, we know like major player in the manufacturing is like TSMC, AMC, later on is Intel and Global Foundries. So the GDS we will be giving to the manufacturing companies. So what how exactly they start is first they make a mask. Later on they will they will work on the base layers. Later on they will go and fabricate with respect to the metal layers. So after fabricating after manufacturing or fabricating, they will be sending it to a packaging team. So Amcor, ASC are the major players. If you see the foundries, the TSMC, the China, Taiwan, the Vietnam, Thailand, or South Korea are the major players. And coming to packaging, Malaysia, Singapore is playing a major role. Even Taiwan is doing that. And good news is like in Gujarat, even there is packaging company which is getting installed in Gujarat. So yeah, and after packaging, the fabricated or else the package chip will be given to a DFT team. They will be checking before sending it to a customer. So without testing, if we send to a customer, the logistics and all, again getting back that parts will be a very hectic. So and for the next batch of fabrication also, it would be helpful. So if they will do the testing before sending it to the customers, and they will, even if there is any issue with the uh, chip, they will check where exactly the issue, and later on that they will debug the issue, and later on they will be adding a patch of the new PDK version will be sent. Like they will debug, they will resolve, and the new PDK part they will add, so that they will be increasing the yield. So if you see over here, coming to the job perspective, so most of the target audience were asking like what and all jobs we can have with respect to the physical design. So coming to the physical design, so the synthesis is one of the focused area. So people can apply for the synthesis role, and PNR is one of the main things. So this is one of the main part. And with respect to sign off, so in sign off also there are various verticals. So one of the main vertical is with respect to timing, STA engineer we call it as. For PNR engineer, scent engineer, and the power engineer, with respect to power. So EM and IR. So we have another domain, another vertical, and physical verification engineer. So the chip has to be manufactured. So we have to follow the guidelines given by the foundry. So foundry will be giving the DRC rules, LVS rules, and antenna rule. So even distance of your tap cells with respect to the technology what we use. So all technology file, TLU plus file, all the details, DRM manuals, all the details will be given by a foundry. So we need to follow all the rules, and we have to clean all the issues. So then only it can be fabricatable. So if there are any shorts, if there are any opens, and if we are going with the fabrication, the functionality will not work. So to make our chip fabricatable, so we need to clean all the things, like with respect to timing, with respect to power, with respect to your physical verification, in that DRCs, physical DRCs, and LVS issues, antenna, everything we have to take care, and later on we have to take out, like we will give the GVS to a manufacturing. So over here, these are various roles, like in various domains we can enter in a physical design. And coming to the EDA tool part, so coming to EDA tools like Synopsys, Cadence, and Mentors. So Mentor is now with Siemens. So Synopsys and Cadence are mostly used. So if you see, for a synthesis, widely used tool is Design Compiler, and for place and route innovus from Cadence, and for some timing sign off, people are going with prime time tweaker, etc. And for physical verification, mostly they go with the caliber. So these are various EDA tools in the market. Why physical design courses are very costly or else very less job opportunities for a fresher is because like the cost of the EDA tools are very high. So companies expect the students from the elite colleges like Ivy League from other countries with respect to analog and certain R&D domains, and or else from IITs. Like Nvidia and all companies mostly look for people from IITs and ITs, or else premier universities, deemed universities. So later on, if you see the tier 2 and tier 3 colleges, so most of the product-based company will not come for a campus placement. So mainly this is because the tool, the cost, etc. So yeah, so they expect students would be trained. So they mostly look for a trained freshers. So this is with respect to the EDA tools, and coming to the IPs. So IPs I have already told, like if I want a standard cell in my design, so I don't design a standard cell as a PD engineer. So there will be certain people who will be working on various cells. They will do the spice modeling. They will characterize, and the optimized results will be added in the. Okay, the same thing with respect to the memory part. So we take this IPs from the IP vendors, and we will utilize in our design. So physical design is a semi-custom. So example, if you see over here, the architecture. So architecture of a Snapdragon. So over here, this is Snapdragon 820 mobile SoC. So CPU is there, GPU, Arduino display related with respect to LTE modem, Wi-Fi spectra, memory. So this is how they are arranged, the SoC. So something like that we will be seeing in the later on stages, how exactly we work on at various blocks, etc. From from send to sign off. So what exactly the PD engineer went to. Okay. So this is the ASIC design flow as we have seen in the ecosystem. So as we mentioned, like first there will be a requirement, like the need from a customer. So system requirements, what is the functionality, performance, power, area, and all will be taken care. So later on, the architects will come and they will make into a small partitions. So RTL design engineer writes the HTL code. Then the RTL code will be checked with respect to the functionality and the spec what the design engineers have been given. Later on, the synthesis, the HDL is converted to gate level netlist. Here is the main part regarding the physical design. Okay, so as I already mentioned, like tools for a synthesis from Synopsys, it is the design compiler. Cadence, it is Genius. Tools for PNR. So it's mentioned as physical design. It is nothing but place and route. For Synopsys, it is ICC compiler, ICC2, and yeah, for Cadence, it is Innovus. And Synopsys has launched one more new tool called Fusion Compiler that will be combined both the synthesis and the PNR. So for timing sign off, we have prime time from Synopsys. Cadence, we have Tempest. Physical verification, Synopsys, we have IC validator. Cadence, PVS, mental graphics, calipers. So this is the flow which we have discussed in the ASIC ecosystem. So first, we need to know what exactly a physical design is. The physical design is a process of transforming a circuit description into a physical layout. So the RTL to a physical manufacturable geometries. So if you are converting that and that manufacturable geometry, the layout, what we get, the GDS will be given to the manufacturing unit. So it describes the position of the cells and routes of the interconnects between them. So during the physical design, all the components are instantiated with their geometric representation. In other words, all macros, cells, gates, transistors, etc. So the main thing what we need to know is, so from RPL we are converting it to the GDS, manufacturable geometries. So we can see the schematic of a CMOS inverter and the layout of inverter, how exactly it looks. So the major thing is the GDS, what the output what we have in a physical design. The major uh, parameters we need to look into is, one is with respect to performance, power, and area. So with respect to performances, with respect to the timing. So if we have a long routes, long nets, etc., so the delay will be more. If the delay will be more, the data capturing also will take a time. So if you see, the frequency will be less. So we have to make sure the frequency of a block has to be increased. So the performance has to be the best. So what we do is, like, first we do with certain utilization, and later on we will squeeze the design and we will improve the utilization, so that our performance also will be increased. Example, even with respect to the frequency. So first example, if we have a written RTL code with it works with 800 megahertz. So what we do, we'll first check with the 800 megahertz and we'll try to optimize and improve the frequency. So the maximum frequency will be the best one. So we'll try to improve the performance. Performance is one of the major criteria. And with respect to the power, as we know, like when we are scaling down, there will be high leakage power, etc. So we will try as much as less the power dissipation. So that is another main criteria. And with respect to the area, so area plays a major role. If we are using a very less utilization, so area is wasted. So much area is wasted that the cost of a chip will be totally dependent upon your size. Example, with respect to area, the manufacturing company charges it. So the more area, the more the cost. So even that is one of the major factor. And if you see any electronic gadgets, etc., so we make sure the area is very less, and a more number of transistors integrated on a chip is more, so that performance, power, and area will be intact. So this is one of the key feature we will be looking for. So before, if you see, like in 1960s, there was the physical design used to named as a board layout. So at that time, very less number of transistors used to be integrated on a board type of thing, and they used to realize the output. Example, if you see in a BTech first year or in the second year, you will be doing a lab with respect to diode as an application of switch. So forward bias, reverse bias in a breadboard, you will be working, right, and rectifier application, etc. So it was something like that, big transistors and minimalistic number of transistors can be realized using the board, etc. So in 70s, as I mentioned, like the integrated circuit came into the picture, and they started adding a good amount of transistors. So the transistor scaling has been started, and we already know the Moore's law. So till 50 years it was valid. So number of transistors integrated on a single silicon chip doubles for every 18 months. So now exactly if you see a small integrated circuit or processor, there are like billions of transistors. So on a single chip. So now everything has been changed. Before synthesis itself different part. So now the correlation has been increased, and now physical design and synthesis has been a single part. And before nearly 70s, they used to call as a standard cell base and route, and later on in 90s they named it as a physical design. And from there, as we know, more number of transistors, the CMOS came into the picture, and the integration, the fabrication facilities, like as from 1987, the TSMC started playing a major role, and they have improvised the technology with respect to mask and fabrication. So more number of transistors were integrated on a single chip. Yeah. So now connection with the logic synthesis has been expanded. So now directly with respect to various AI algorithms and all the tools which come, like the CAD tools now mostly use the AI part in their algorithms to give accurate results. So if you see now Fusion Compiler, like it has been merged both the Synth and PNR together. So coming to the physical design flow. So these are a few things. The flow is, so the flow starts with the floor plan, followed by power plan, placement, CTS, uh, routing, and later on timing sign off, and uh, physical verification. Later on, if everything is clean, we will go to the power EMIR and take off. If there is an issue over here with respect to cycle, we will do repeat the ECO cycle, and we will try to fix the DREs. So DREs are nothing but max plan, max cap, max fan out, and even setup and hold also we will be trying to fix in the ECO cycle. Then we will be giving to a EMNIR. So this is a PD flow. We will be seeing each block in later slides. Yep. So this is the first part in PD. So synthesis. So we have various type of synthesis. One is logical synthesis, low power synthesis, and placement aware synthesis. So we will be using for placement aware, we will be using deck pipe. So first we'll talk regarding the logic synthesis. So logic synthesis is a method to convert higher level abstraction to a lower level abstraction. Basically, the RTL design as an input, as a Verilog file, which will be written by the RTL design engineers, which is verified by verification engineers, will be taken as an input, and we will be converting that RTL to a technology dependent optimized gate level netlist. So this is how the things work, and we will be seeing what and all steps are involved in the synthesis. Excuse me. The gate level netlist can be optimized, and the major things which I have told, like area, speed, testability, and these are a few major important factors we will be checking in our synth. So I have told, like for a logic synthesis, RTL netlist, SDC, and libraries are the inputs. And if you see over here, for physical aware or its placement aware synthesis, we will be using a TLU plus file, and floor plan def, where it will be having the information with respect to the physical information of boundary, and even with respect to macros, etc. Okay, so and the TLU plus 5 will be added. For a low power synthesis, UPF will be added with that. So these are various synthesis we will be doing. So first, in a synthesis, the output of the synthesis is optimized gate level netlist, STC, and UPF. So in optimization stage, the technology mapping is performed by the synth tool. So we will be seeing in the next slide how exactly the things are. And in the right side, you can see we can see a diagram where I'm on. So in optimization, what exactly it does is the number of levels or the number of gates will be optimized, and after optimization, there will be a mapping. Yeah, this is our main process. So if you see, we will be taking HDL source. You will not see any AND gate, etc. in the HDL source. So mostly if it is written in RTL behavioral. So what exactly we'll be doing is the RTL code is translated. Translated to a generic netlist, the GTEC file, which is technology independent. Later on, that GTEC file will be optimized, and with respect to power, area, etc. And later on, after doing the optimization, the mapping with the lib what we are using. So if we are using a 5 nanometer lib, so with respect to that, it will get mapped, and we will be getting the technology dependent gate level netlist. So if you see over here, synthesis, the main steps over here are translation, optimization, and mapping. So translation will convert HDL to the GTEC. The optimization will, with respect to power and area, it will optimize, and later on the mapping with respect to the lib which we are giving. So it will convert a technology independent netlist, a generic netlist to a technology dependent optimized gate level netlist. Yeah. So the major goals for a synthesis is the timing, area, and the power. And we will even do the sanity checks before giving it to a PNR. So to check whether if there are any floating issues, if there are any combinational loop, if there are any multi-cycle, black boxes, multi-driven nets, etc. So we will be checking all those things, and if everything is clean, we will be giving to the next. So if we find any issues with respect to multi-driven nets, or else if there are any black boxes, we will be black boxes, or else any combinational loops, etc. We will be reporting to a RTL team or RTL team. So if we have a combinational loop, again there will be a problem when we are doing the timing analysis. So STA tool will not give a proper result with respect to timing. So coming to a block level implementation, so these are the various files. So netlist by the output of the synth team. The timing constraints over here, the output of a synth we are taking, but normally SDC will be coming from the design, the top level team. So the design people will be giving us. So later on, the logic library. So as I mentioned, the standard cell library, or else with respect to like analog IPs, or else some digital IPs, soft IPs, and all we will be getting from the vendors, library vendors, and physical library from vendors, and TLU plus and technology file by a foundry. And even we will be getting something like DRM, we will be getting antenna rule, LVS rule, LVS rule, everything we will be getting all the details from a foundry. At the end of the day, we need to manufacture, fabricate the chip, right? So we need the files from the foundry. So if you see house floor plan and a full chip floor plan, so this is one of the critical step in the PNR. So if we do a bad floor plan, If you do a bad floor plan, the performance will be less, the delays will be more, and you can't sign off easily in the later stages. So timing closure will be a very tedious job when if we are doing a bad floor plan, and even area would be very high, and the cost with respect to area, with respect to manufacturing, will be very high. So that is also one of the major issue. And power. So power also will be very high if we are doing a very bad floor plan. And even cleaning the physical PV checks, like with respect to D-axis, physical D-axis, LDS and all, will be very tedious, and the congestion and all, higher and all will come into the picture if we are doing the bad floor plan. So in this picture, you can see the analogy between house floor plan and a full chip or its ISIC. So if you take the house boundary, it's something like the die boundary over here, and the rooms in house floor plan are something like blocks, each block in a full chip. Okay, so it is similar to that. So what exactly we do, and the basic difference between the block level floor plan and the chip level floor plan is, in a chip level, in a full chip level floor plan, what we do is we do a partition into a smaller blocks, and we will be keeping it. The partition is the only thing, and rest of the things are same. So example, in a full chip, these blocks are the major players, and in a block level, the macros will be the taking place as a blocks over here. So that is the only difference, and rest of the things from place and block, everything will be similar. So this is the analogy between the house floor plan and a full chip floor plan. So uh, you can see the red colors over here are like a block placement, and over there it's a placement. So we have a iPad boundary, and later on, if you see the room floor plan versus a block floor plan. So if I in a house, if I take a single room, so it is something like a block of a full gym. So example, we will be adding a furniture, right? Bed, table, cupboards, etc. Something like that over here in a block level. We will add macros, various type of macros, and later on we will be adding with standard cells, physical only cells, etc. So this is a certain analogy between the room floor plan and um, the block level floor plan. So first, in a block level floor plan, what exactly we do is, first we will initialize the boundaries, and we will give a shape. Later on, we will be adding we will be placing the IO ports. So we will be placing the IO ports, and we will fix it. So after placing the IO ports, we will whatever macros have been instantiated in our article code, we will be taking those. Uh, uh, we will take that macros, and we will be placing by using the macro placement guideline. So if you are placing the macros using the macro placement guidelines, we can easily clean the issues later on, like DRCs, etc. If we are not using a macro placement guidelines, so the PPA will not meet. Even we can't close the timing and the PV part, and it will be a very tedious job later on. So we use a macro placement guidelines when we are placing it. So now if you see, like there are only 5 macros in my block, but there will be certain blocks with 200 macros, etc. So placing a macros will play, and it will be a very tedious. So now there are so many machine learning based algorithms coming into the picture, which have been integrated in Fusion compiler or else the ICC tools, where by using those ML placers, so we can place the macros by using a script. So we can use that, or else by using the macro placement guidelines. So the first what we do is by seeing the hierarchy. So all the related hierarchies will be keeping together, and later on the next important point to be taken care is with respect to the fly line analysis. So even in a fly lines are nothing but a connectivity. So the macro we will be giving a priority with respect to the connectivity. So first we will be giving importance to a macro to IO port, next macro to macro, followed by macro to a standard. So by using this things, we will be placing the macros, and we will not place macros in the middle of the core area. So if we are placing the middle of the core area, the macro will internally will be having the transistors, etc. Even it will be having a metal layer. So the macro will take example, if macro is there, example there is a macro one is a SRAM. So SRAM is designed using M1 to M5 layers. So if I use that macro and place in the middle, so standard cells might sit left and right to the macro, and later on what will happen is when we do the physical connectivity, the standard cells have to use the higher metal layers for a less routing, or else they have to detour. So the availability of a higher metal layers will be very less. And if we are doing a detouring, the net length will be increased, and we will again face the DRB like max cap, max tran, and even the delays will be very high. And to meet the timing will be problematic later on. So it's not advisable to place a macros in the middle of the core area. So later on, after placing the macros, we will be giving certain space between two macros. We call it as a channel spacing. So why we give a channel spacing is later on, if you want to when you are doing the CTS or it's a routing, if you want inverters and buffers to be routed in the place. So what we do is, and that inverters and buffers need power VDD and VSS. So what we do is we will leave a certain gap between two macros. So even if the pins are not in the same direction, what we can do is we can embed the macros also. So we can do that. So even we use a keep out margin. So why we do a keep out margin is if my standard cells in the placement steps, my standard cells are placed near the pins of my macros. So again, there will be congestion and routing issues. So what we do is we will be doing the padding. So in certain places, we call it as a keep out margin. Some people will call it as a halo. So we will be giving to our macros. So the same padding, if we are doing to a standard cells, we call it as instance padding, or else instance padding, or else we call it as a cell padding, or else an instance padding. So we do that later on when we have a condition. So over here we only do for a macros, and all the physical only cells, and even the IO buffers, standard cells will be there in the origin even at this stage. So only macros and pre-placed cells like end cap cells, you can see R and L in the block. So these are like end cap cells and or else a boundary cells. So why we use end cap cells and a boundary cells is to avoid the well proximity effect. So this well proximity effect will be occurred while doing the fabrication process. So when we know, right, when if we want to fabricate, first we take a wafer, then later on we will do the doping, then on that like N plus and P plus substrate we will be taking. Later on we do the oxidation, etching, UV radiation, and with respect to ion implantation. Even if you are working with a smaller nodes, we can go with ion beam, FIBs, etc. So over here, what exactly things when we are doing ion implantation is we will be doing ion implantation with respect to 7 degree, etc. So it depends. So at that time, the dopants will be accumulated at the corners when we remove the polymer and all, right. So mostly dopants will be accumulated near the corners of the rows. So what will happen there is because of this dopants, the threshold voltage of that bells and wells will be increased. So if that is increased, and even the IV characteristics will be changed. To avoid such issues, what we do is we will place a boundary or its end cap cells which doesn't have any logic functionality with respect to our design. So for a protection and to protect the well proximity in a manufacturing stage, we will use this encapsulates in a floor plan stage, and even we will be adding tapsels. So tapsels to avoid the latch up issue. So what exactly thing happen is with respect to the technology what we use. Like example, if we use a 5 nanometer technology, or else if we are using a 7 nanometer, 3 nanometer, or 14 nanometer, with respect to the technology, the spacing of tap cells will be given by a foundry. So we have to make sure the spacing must not be exceeded than the limit which have been given by a foundry. So what exactly thing happen is if we are giving more space with respect to the tap cells. So the tapping will not happen properly, and certain cells might get a latch-up issue. So we already know what exactly a latch-up is. When there is a ESD or a certain spike in voltage, so the unwanted parasitic BJTs in our MOS will be triggered on, and later on there will be a low resistance path from VDT to VSS, and it will be like a loop, and later on the chip will get there will be so much power dissipation, and later on chip will get failed. So to avoid that, what we do is we follow the guideline given by a foundry, and we will make sure it will not reach it will not exceed the value given by a foundry. So that is with respect to the pre-placed cells which we will be adding in floor plan, and we can even add certain space cells in over here. So how exactly space cells will be used is after doing the base tapeout. So we know like there are various layers. So base layers are with respect to the transistor related stuff with the P diffusion and diffusion and etc. All the poly and the buried contact. All these things comes under the base. So what exactly is like the base layers will be fabricated. We will be fabricated first. Later on, the metal layers from metal 1 to MRDL will be fabricated later on. So each layer will be having a mask, and they will be fabricated step by step. So while after doing a base fabrication, and when we are checking the timing, so if there is any change in ECO, when we are doing a timing sign off after a base tape out, if we find some issues with respect to the logic, we can't if it is a minor issue, what we do is we utilize this space cell which has inside various types of functionality, so that we will be using to fix the issues after the base tapeout. So these are the pre-placed cells which can be used in a floor plan. So main thing is the heart of a PD is the floor plan. If you are using the guidelines, and if you are following everything, and if you do a proper floor plan, later on we will not have issues with respect to the VRC, style VS, the timing, etc. The congestion, IR drop, etc. So we have to eradicate that, and to remove the complexity later on, what we do is we have to do a proper floor plan. So later on is the next stage for the floor plan is power plan. So in my core area, uh, I have a cells, various cells like macro, where I have macro standard cells and all, right. I'll be placing later on the standard cells, physical only cells, buffers, and so many things will be there. So all those components need to get a power, right? So in power plant, what we do is we will create a power distribution network. So the power distribution network with respect to VDD and VSS. So we will create the network, and it has to be like the power has to be distributed to all the components present in the design. So the major things we need to check over here is with respect to EM and IR. So electromigration. So what exactly things happen with the EM is and if a wire is there, if there is a high current density. So if there is a high current density, the electrons will flow, and the electrons, what exactly things happen is it will make sure there will be, with respect to the movement of electrons, even there will be the heat generated. So that heat, what exactly it will do is it will break the bonds, metallic bonds in a metal, so that metallic bonds will get broken, and the atoms in the metal will get displaced. So the place where exactly my atom is dislocated, we call it as a valley, and the place where exactly my atom is sitting or it's deposited, we call it as the hill. So what exactly thing happen is down the line, because of this ERP, there will be opens and shorts. That shorts might create stuck at 0, stuck at 1, and with respect to opens. So what we have to do is we must take care my EM electro migration we have to be fixed, minimalistic. So what we do is we will be using the wider metal layers. So that is why if we have a metal stack with M1 to M9, so we will be using M9, M9 and M8 for a power. So we know, right, M1 will be having a less width and M9 will be having a higher width. And down from M1 to M9 down the line, what exactly things happen is the width of the metal layer increases. So we know resistivity is equal to rho L by A, where if area is more, my resistivity is less. So we have to make sure to eradicate that EM. So we need to take a wider metal layers. So and the IR drop. So we know no metal or its no component is idealistic in nature. So even a metal layer will be having certain resistance and capacitance. So with respect to if example, if I give a source voltage as 5 volts, and the output, if you see, the 5 volts might not be my output. There will be certain drop due to the resistance and capacitance of my net. So I may not get to a perfect 5 volts. It might be like a 4.8, 4.9, something like that. Okay. So if there is more voltage drop, if there is more voltage drop, there will be more delay and there will be issues with respect to timing. So if it is exceeding more than threshold, what exactly thing happen is my transistor only will not switch. So at that time, what exactly will happen? The functionality also will be changed. So what exactly we need to do in a power plan is entire power distribution network has to be covered. All it has to cover all the components. Every component has to get a power. I have to have a minimum EM and a minimum IR. So this is with respect to the power plant. These are there are so many things, but these are the key points because taking time as a constraint. So I'm telling the main things. So even we will be checking the PGDRCs, etc. So PV role will come into the picture, and those people will be helping us with respect to cleaning the PGDRCs, or else in certain companies, even a PGDRCs will be cleared by the PD engineer. So next is with respect to the placement. So till now, what exactly we did, we have made a boundary core boundary. Later on, we have placed my IO ports, followed by macros have been placed. Even I have placed my encapsulates, tab cells, page cells, etc. So later on, if you see, my standard cells are placed in the origin. So in the placement stage, what we do is it is a process of placing the standard cells in the rows created at a power plant stage. So we will be having sorry. This the one part, like example in a diagram, this is a full chip. So these are the pads which we can see, blue and red. Yeah, the blue one and the red one we can see over here, right? So in the four direction, these are the VDD and VSS part. So first from there, the power is given to the supplied to the rings. So first it will go to the rings, then to the stripes. As we can see, these are the stripes. These are the stripes. These are the stripes. The vertical one. So from stripes, it will go to the rails. From rails, the standard cell will get up. This is the power distribution. If you are working with the block level, we can only see the stripes and the rails. So if you are working with the full chip and all, you can see the rings, etc. Okay. So this is how the power distribution will be done in a chip or also a block. So yeah. So placement is a process of placing the standard cells in the rows created at a power plant stage. So what we do is by using the timing driven or else like congestion driven, power driven, or else area driven. So these are a few techniques. There are different algorithms with respect to that in the back end of the tool. So by using those things, what exactly we do is by using those mechanism, we will try to place standard cells in a core area. So this is a major role of what we do in a placement stage. Okay, so when we are doing a placement, so first what exactly thing happen is initialized placement will be happening. So all the cells will sit on a standard set. So some cells will be overlapped, some cells will not sit on a row side and all. So what we do is we do a legalize. When we do the legalize or it's a detailed placement, so what exactly things happen is the all the legality issues will be gone. There will be no overlaps. The orientation, everything will be in a proper state. So later on, after placing the cells, what we do is we will go with the quality analysis. So QOR analysis. So what exactly we do is the main checks we need to check in a placement is after placing the standard cells, we will check by using the estimated routing. There will be estimated routing. With respect to that, we can check the timing. So if there is very much high timing, like my timing is violated with high value. So what exactly I will do is I will check where exactly the issues are. So there might be a module splitting, there might be a bad floor plan, there might be with respect to the condition. There are so many things to be checked in the placement stage. So example, so even we need to check all the cells are legally placed. After doing that, with respect to the congestion part. So if available routing layers are 10, if I require 20, so 10 extra are needed, right? So you will be having a condition. So to eradicate that part, we will be even seeing the congestion part. If there is more congestion later on stages, we will be facing the issue. The DRCs, etc. We will be it will be a very tedious job to clean that issues. So what we do is yeah. So as with respect to time, yeah, with respect to time, like I'll be going later. happen. So in placement stage, we will be checking the cell density, pin density, and congestion. So if the cell density is very high, what we will do is with respect to cell if it is a global congestion, we will check whether I can spread out the cell. If there is no space, so what we do, we will increase the size of our boundary. Means like the utilization we will reduce. Utilization percentage we will reduce, so that we will get more core area and we can place the cells. If there is a global condition. So if there is local conditions, we can use a partial blockages. If there is a cell density, we can use a partial blockages and we can spread that out. And if there is a pin density, we can use the cell padding or else instance padding, and we can spread the cells and we can reduce the pin density issues. And if there is any timing setup is not meeting, so we need to check whether there are any module splitting, etc. If there are any module splitting, we can use a bound approach and we can fix that issues. So this is with respect to the timing. And if you see over here, the floor plan and power plan, afterwards we do the uh, placement, then this output we will be giving to a clock tree synthesis. So later on, the optimization will be done with respect to PPA, performance power area. So that output will be given to CTS. So in CTS, what exactly we do is we will be in my design, there will be so many sequential cells, right? So all the sequential cells will work with respect to a clock. So here we will be creating the clock network. So the clock tree we will be creating in a clock tree synthesis. So we will be using a clock inverters and buffers. Why clock inverters and buffers is they will have a equal rise time and fall time. So if there is unequal rise time and fall time, if you are not using the normal buffers, if there is a number of logic levels are increased. So if you are using the normal buffers, what exactly can happen is later on stages, entire flops like the sync pins, all the sync pins might not get a flop. There might be signal deterioration. The minimum pulse width issue will come into the picture. So we have to make sure we have to use a clock buffers and clock inverters in the design. So this is one of the main thing. So over here there are various types of topologies or some methodologies in plot tree. Plot tree. That's why building a plot tree. So what we will be doing is uh, if I am working with the high gigahertz systems like 5 gigahertz and all, we can use the best methodology will be our mesh, clock mesh. But with respect to power, it is very tedious, and we with respect to clock gating and all also later on stages it will be little tedious. But for a high gig systems, we can go with clock mesh or else H tree, and with respect to lower gigahertz and all, we can go with the faster or else H tree. H tree is one of the most used. So over here we have to mainly concentrate on the latency and the skip part. So these are the two factors which we have to take care. So the things whatever we give in HDC has to meet. So we have to check whether our a clock after creating a clock it is meeting the requirements or not. So these are a few things. And example, if you see this is a clock pin, and from clock pin we are giving it to a flip flops, all the flip flops. So all the sequential cells need to have a clock. And here the major thing you need to see is my skew has to be minimalistic, near to zero. Okay, it can't be zero. We can't make it zero, but it has to be minimalistic. And my latency also has to be low. So we need to maintain that. Okay. So these are the two factors which we will be mainly focused on in the progress synthesis, and we will be using the NDR rules. So if the user wants to use his own rules other than the default rules, like example, like if I'm working with low frequency signal, low frequency design of 50 hertz or it's 100 hertz. So for certain special applications, so you can use double width and four spacing, etc. Because the small coupling cap also will create a crosstalk. So there are a few things we need to check over here. We need to make sure there is no crosstalk. So to avoid the crosstalk, we can use shielding, or else we can increase the spacing. So these are our few things which we need to know. Yeah. So the things with respect to the routing and sorry, with respect to CTS, and the next stage after CTS is routing. So in routing, what exactly we do is in synthesis netlist, we will be having a logical connectivity. So in logical connectivity. So now we have placed the macros, we have placed the power routing is done, clock routing is done. Now signal routing has to be done, right? So what we do over here is after placing all the cells need to be having the signal, right? So what we do over here is we do the signal routing. So physically, logically, the connections will be there in my netlist after doing the synth. So the same thing has to be connected over here. So physically, by using the metal layers, we will be connecting all the cells. So there are three stages in routing: global routing, track assignment, and detailed routing. So after doing the routing, we need to take care with respect to the design rule check and the layout versus schematic and routing part. So even antenna and all also we will be checking. So these are the two main, these are the two main things we will be checking. So these details we will be getting, the Rolex we will be getting from the foundry. So if you want the design to be fabricatable, so we need to fix this part. So most probably spacing issues, enclosure, opens, shorts, etc. You will be facing over here. So we will be have to clean those things. Later on, the routing DB parallelly can be given to the various teams, like we can give it to the timing sign. So here we didn't focus much on the timing part. So we do the timing sign off by using the prime time trigger, etc. So we will try to fix the DRVs and the setup, hold and the setup. So by using various techniques like buffering, PD swapping, promotion of higher metal layers with respect to setup, clock pulling, clock pushing, so many various techniques we will be doing in timing sign off. So we will run ICO cycle. We will physically implement in ICC2. We will take the inputs, all the inputs from the PT. So we'll do that part, the timing part, and the other part. What we do is the physical verification. So we will be having all the details we will be getting from the foundry. So what exactly we do is if we are not if we are not following that rules like the DRCs. Example, I will list few things. It's all the metal layer details. Like example, my metal 9. So it has certain width. It has certain spacing. So if we are not following that spacing issues, we'll end up with the crosstalk. We will end up with DRC issues later on when we are fabricating a layer by layer. So you can't fabricate it properly. Okay. So that is why we need to clean all the DRCs and LVS in this stage. So due to the time, I'm rushing up. So there are so many things we will be doing over here. So next is antenna roll deck. So antenna roll checking. So if the transistor will be having a long metal metal layer. So what exactly think happen is so many charges will be accumulated on the metal layer, and there might be the oxide breakage. So the cell will not work. So we will even get the antenna value, the antenna ratio. So it's nothing but a metal ratio by the gate plus diffusion ratio. So if it is more, there will be more charge accumulated on a wire, and it will affect the oxide layer. So it will create an issue. So to avoid that, what we can do is we can use antenna diode, jumpers, etc., to avoid the antenna issue. So as I told you, like if there are any, if we are in the floor plan stage, I have told like something with respect to tap cells. If the tap cell distance is very high, there might be a latch up issue. So if you want to check if there is any latch up issue in my design, you can check with ERC. So you can find that in ERC. So later on, we will even do the EM and IR with respect to power. So the main challenges in physical design, if you see the new process with the new process technology, the number of transistors per unit area doubles. So now, if you see, now we are in 3 nanometer, and there are so many second order effects. And now, what exactly from CMOS we went to FinFETs, even shifted to GAA, and certain people are working on quantum-based devices. Certain people are working on spintronic devices, so magnetic tunnel junctions, gate all around double gate transistors. So many various architectures people are working on to integrate more number of transistor on a single chip, and the congestion. If there are more transistors, the congestion, cell density, pin density, signal integrity will be very high. We need to take care of the leakage power, and because when you are scaling down, the leakage will be playing a major role in the short channel FETs. So that is one of the important factor we need to take care. And even the heating issues, that is also one of the major parameter we need to look into, and the timing part. So timing with respect to if a high gigahertz systems, it is very tough to clean timing. So we need to take care about the DRVs and setup and hold, coming to the area and the runtime. So if you see the current trends, so first it started with the metal-based semiconductor devices, followed by bipolar transistors. After bipolar semiconductor transistors, later on in 1980s around, the bipolar transistors have been replaced with a MOS technology. Now, if you see the MOS is the CMOS is replaced with the FINs, the GAs, and all. Like later on, we don't know what new things will come into the picture. Still, research is going on with the quantum based transistors or else magnetic tunnel junctions, etc. So the major applications are high performance computing, mobile computing, autonomous sensing, and computing. So these are the current trend. If you see from 3 micrometer at around the 1980s, now in 2023, it's somewhere around 3 nanometer. So this is the end of my talk, and Rahul, our BDM manager, he will be taking care of the careers perspective and more details he will be giving you. So over here, like some students have asked regarding the jobs, like till last month, the job uh, yeah, now the job market, like currently with respect to physical design, the 3 plus 5 plus years hiring is going on. Most probably from Jan or Feb, the trained fresher jobs will be started. So now For physical design, the major subjects, the prerequisites you need to know is with respect to CMOS. CMOS plays a major role for the physical design. Later on, digital design and TCL scripting are one of the major things which you need to know. Yeah. So Rahul will be taking over the career perspective, etc.
Thank you so much, Dr. Abhinav. That was a wonderful session. Once again, I'm happy to connect with all of you this beautiful morning. So I have connected again to give you some insights about the career opportunities in semiconductor industry. So once again, I'm Rahul David from Chip Edge Technologies from Bangalore. So thank you for posting your questions here. Like all your questions will be answered after this session. All the technical questions will be answered by Dr. Abhinav. So like continuing with the session, now I'm going to give you some insights about the career opportunities in semiconductor industry. So first, like we'll see like what IESA is saying about future of VLSI. So somebody who doesn't know what IESA is, it's Indian Electronics and Semiconductor Association. This is a government of body institution. So this will act between a bridge between the universities as well as the industries. So so they are saying like this is the fastest growing sectors in Indian economy. So Indian household holds more than 20% of global semiconductor design engineers, and its goal of generating 1 trillion US dollars by 2025. And the best part is there is only 5K employable workforce today in ESDM. So by 2027, they are expecting like 85,000 opportunities in electronic system design and manufacturing. So there is a wide open opportunity for like whoever is interested to become a VLSI engineer at this stage. So next thing is, so how to how do service companies or product companies like find their candidates? How do you pursue career in VLSI? So campus management, campus placements happens mostly with the like tier one colleges. So they do hire interns and give them full time jobs. And after that, in case if you don't get placed in your UG, you will do PG. So in which they also select students from premium institutions like IITs, NITs, triple ITs, BITs, VITs, and even in Manipal. And few students, what they do is they will join college which has good placements opportunities in VLSI, or they do masters from US or European universities. And the last way to go into VLSI career is join any VLSI training courses in any institutions. So the next part is about chip edge. So now we are talking about opportunities. Now I want to say you like how chip edge can help you get you this opportunity. So about chip edge, we are a VLSI edutech training company. We are in the market from 2012, and we are like train more than 4,500 engineers. And we have partnership with close to 200 plus hiring companies, service as well as product companies, and we give 100% placement support. So these are our courses. We offer courses to freshers and working professionals. So for freshers and working professionals, we offer courses like specialized courses covering entire digital and analog VLSI design circle. And this is offered in weekend and weekday classes, and placement assistance and mentorship is given for them. As well as we offer courses for corporates as well. So corporates, we do tailored specified courses. And for this is for new hires and as well as for laterals, and this is also done in weekdays as well as weekend classes. And for educational institute, we train the faculties, we train them to improve their skills, and also we do certification programs for students and delivered in college. And we also do internship model programs for students, and that would be a 4-week internship models which we have introduced from 2024 from this January. Now I will teach you like how do you choose the right domain in VLSI. So these are the domains which are open for the VLSI engineers, which is digital electronics, analog electronics, CMOS devices, and programming. So say like you are good at digital electronics and you are good at CMOS devices. You can easily choose physical design and you can become a physical design engineer. So say like you are good at analog electronics and CMOS devices, you can become an analog layout engineer. And if you are good at CMOS devices and analog electrical as well as digital electronics, you can become a DFT engineer. if you are good at programming and digital electronics, you can become digital verification engineer. So this is how it works. So I hope everybody knows what is physical design, since Dr. Abhinav has already told you clearly about what it is. So let's going to the next thing. This course is offered online. So the offline. So these are the courses which you are offering for the students as well as working professionals. So this would be offline courses. So we offer courses in physical design, design verification, and design for test. And all these courses will have 600 hours of interactive learning sessions, assessment after every module, and we do offer placement assistance. And the best part is you can do it in no cost EMA as well. So physical design and design verification courses will be like 6 months, and design for test course will be like 4 to 6 months, depending upon the courses you select. So next is self-paced program. Say if you cannot do an offline program, you are committed to work and you cannot come to Bangalore or do these things. We are offering these courses in self-paced model also. So these are few of our courses. So these are our course domains. We offer courses in RTL design. We offer courses in design verification. We offer courses in design for test. We offer courses in physical design, synthesis, sign-off, ST, and LEC. And these are our upcoming courses. We have formal verification, TCL scripting, and Python scripting as well. We offer close to 45 courses in this session. So I will share you the link for our self-paced learning courses as well. So you can have a look on it. And also we do offer some free courses there. So anybody who is interested, who want to taste how the courses are, you can go there, you can register yourself, and you can start doing the courses. The next thing is these are our upcoming VLSI courses. So today we are starting a batch which is live online. So which will be for design for test. And tomorrow we are starting another batch that is for physical design. And we have a design verification which is on 6th January. And these three would be live online courses. And the 22nd of January we are starting 2 more courses, which is design verification and physical design. And this is purely offline courses. This would be 5 to 6 months of courses. So next thing is how it works. So it's say you are interested to join our program and you wanted to know how it works, right? So this is how it works. First, you have to register through our website, and after that, our advisor will contact you and help you to choose the correct course for you. And after that, you have to clear the eligibility online test. And after you clear the eligibility online test, you will be enrolled for the program. You can complete the course assessments and projects. Once you complete the course assessments and project, you will get placement training from the industry experts. So once you get placement training, you will be scheduled for interviews from VLSI product or service companies. So after that, you will get your job offer letter. So speaking about job offer letters, I want to speak about your growth, salary. So basically, a fresher who is a PD engineer or a custom layout engineer or a DFT engineer or a verification engineer, their starting salary will be from 3.5 to 15 LPA per annum. So we have proven engineers who have already got placed for these salaries. So when time passes, maybe 2 years or 4 years in this field, you will learn more than an IT guy who's earning now. So that is what the market is for VLSI now. So since they are expecting around 85,000 jobs, and they are hoping around 1 trillion US dollars to be done by 2025. This is the growth for VLSI engineers in the future. So these are few of our hiring partners. As I said before, we have 200 plus hiring partners with us. These are few of our hiring partners. So once you complete your program, we will be scheduling interview with these companies, and they will come, they will recruit you, and you will get placed with these companies. So this is our contact information, and I will also post my URL, our company's registration link, our inquiry form there. They will recruit you, and you will get placed with these companies. So this is our contact information, and I will also post my URL, our company's registration link, our inquiry form there. And now I will be sending you the registration form link as well as the URL for our learning platform. You can just look into it, and in case if you have any queries, you can always contact me back. Dr. Abhinav will answer your questions. Whatever questions you have posted in the questionnaires group, it will be answered now. In case if you have any more questions also, you can post it.
So somebody asked regarding the UPF. So I have posted that. Kindly good morning, sir. As a fresher, we will be assigned to a specific role like STA engineer, PNG engineer. So, certain companies like they will directly treat like we need a STA engineer or something like that, or else like in courses, what exactly they do is they will teach from synth to sign on. So after going there, like with respect to the availability position and all, they will take you. So if you are lucky enough, they can directly put you in a STA engineer or else a PNR engineer and synth. But PV separately they will mention like we are hiring for a PV role. So PV need to have more expertise with certain more checks other than what I showed. Like even DFM, DFI, ERCs and all will be coming into the picture. So and even if you see with respect to the growth, the salaries of PV will be little lesser side compared to the STA. In entire VLSI, the people with the STA with the good concept will be earning very high salaries. So this is with respect to the fresher job. So it depends like the service-based company if you are entering. So they might say you to run the entire flow. If you are entering certain company like AMD, Intel, etc. So they might give you only extraction part, or else they might give you only the PNR. They might give you only the timing, or else synth. So you might be little focused. So like little smaller companies, or else certain companies, what they do is they will say you to run from first to last. It totally depends upon the project position availability. Yeah. Like as Rahul nicely explained with respect to the growth in the physical design in future. So, example, if you see, like as a fresher in fresher for a fresher job for a BD in a service based, so they might get something like 3.645, etc. But in a product based company, there are people who got a starting salary of 18 lakhs, 15 lakhs at chip edge. So these totally vary with respect to where exactly you place. And coming to the growth perspective, like growth, if you get 10 lakhs for IT engineer as a fresher and 3 lakhs as a PD engineer as a fresher, after 10 years it will be other way around. So, and with respect to jobs, the number of jobs, somebody asked a question. So, it will not be as much as IT or else verification positions. But after DV, the more number of jobs will be there for PD. Later on, very minimalistic jobs will be there in analog design, not a layout design part, etc. And architectures, etc. So coming to the question, do AI affect the physical design? So even now we are using certain AI algorithms and machine learning based algorithms at the back end. So yeah, so we are using so many AI tools. The mainly, if you see with respect to AI for a verification, so much space is there with respect to AI, and with respect to physical design, the CAD perspective is more. So CAD perspective in the sense like we will be using a different places, algorithms, and all right. In the back end, it will be used for the CAD team who makes the tools. So like you don't worry like if AI come into the picture we will lose our jobs, etc. Because so timing manually we need to clean certain issues with respect to DRCs, etc. We need to clean the optimization with respect to the analysis and all. The tool can't do totally. So AI can't affect the physical design, but it will give us a positive feature where the new algorithms will give us a more accurate result, so that yield will be more. So in that perspective, yeah, AI will be affecting positively with respect to the CAD, and with respect to physical design, there is no issue, no worries. And coming to the other question with respect to the UPF. So with respect to UPF, I have mentioned. So yeah. So these are the things. So any other questions? So if you have a multi-voltage design and certain things, the power details and all, we will be giving the retention strategies. We have various retention flops, level shifters, so many things, clock gating, power gating, all those things, different isolation strategies and all will be there in our UPF file. It's IEEE standardized file. So by using the typical scripting, we use that UPF. So if, the main thing is for the low power designs, etc., we will be using. So yeah. So is there any other questions? Satish, that what the questions? Yeah, so regarding the placement, as currently the status with respect to PD, like recently, Quest Global, certain people got placed in Cadence, Intel, etc. Now only the placement is getting started. Like currently, with respect to PD part, 3 years, 5 years plus experience jobs. Hiring is going on. Most probably in Jan or February, the fresher hiring might start. So we can see the trend, from the downtrend and the layoffs. Now it has been standardized. Now it is moving positively. So yeah, so no worries, Satish. So most probably, like in December end or January, you will be getting messages in Supershot. Yeah. Yeah, he's doing training for physical design engineer help to get a job. So if you are in elite colleges like IITs, triple ITs, NITs. So what exactly you will be having is you can get a direct placements in NVIDIA, etc. But most of the companies will not spend much time and money with respect to tools and with respect to cost, with respect to manpower for the training purpose. So the companies will not reach out the tier 2, tier 3 colleges for PD and VLSI, mostly in VLSI weapons. So they expect students to get trained. So that is why they ask for the trained fresher. And here comes the training institutes, which play a major role with respect to the training. So PD training will help you so much, because concepts are fine, but the hands-on experience with the tools has to be there. So that is why PD training will be very helpful. Yeah. So I think I've answered why there are very less vacancy at the companies for PD. Yeah, as I told, the jobs with respect to PD will be like in perspective of VLSI, it has a second highest number of jobs. But if you see with the respective total picture with respect to IT and all, we have a very minimalistic. And even with respect to process, there are very negligible jobs. So most probably we will be having a DV. Highest number of jobs will be there in a verification, followed by PD, followed by DFT and PD. Yeah. And for PD also, we can the PD trained fresher can apply. if he knows certain concepts with respect to DRC, LVS, CRC, PERC, etc. Yeah.
Maybe tested is not right. No, now I said.
Yeah. So, Tibet, any other queries?
Here.
I think I have answered most of the questions.
He's not accepting access.
Well, yes, please. And thank you so much.
Hi, Mr. Abhinav and others. Thank you so much for this session. So, hi, I have posted our website link as well as our e-learning platform links. So, anybody who's interested, like you can go register there, or you can have a look on our website as well as the free courses are available there. You can, if you want to have a look on our free courses, you can always come to see that. So, this session, I hope like it would be very useful for people. So yes, in case of any questions, like I have shared my email ID as well. You can just post your questions to me in email. In case of any assistance with the program or any technical questions or anything, you can always post us. So actually, no, we are in the urge of like ending this meeting, as we have supposed to end this meeting before 12. So thank you so much thank you so much for your participation. And after this, like we will be having. Like you will be getting a participation certificate from this as well, so you can download it. In case of anything, like you can always contact me. I'll put my email ID and my phone number there. So thank you so much for your participation.
Thank you everyone for joining. I'll be ending this session. I posted the phone number and the email where you can contact, and some of the students who have raised the query personally on chat, our team will be getting in touch with you. So thank you everyone. Thank you, Dr. Avidav. Thank you, Rahul.
Yeah, thank you so much. Yeah, thank you so much.